We present our work Domain Adaptation of Semantic Segmentation Models using weak labels. Semantic segmentation is a task where, given an input RGB image, we want to learn a model G to predict the category of every pixel in the image. In current state-of-the-art methods, the model G is generally convolutional neural networks, which learns using pixel-level annotations. However, the segmentation model learned on one dataset, say the source, may not generalize well to images from a different distribution, the target, due to the domain gap between them. Thus, the model G needs to be adapted to the target images. But as annotations may be expensive on the target side, we want to adapt the model from the source to the target with none to minimal annotation cost. Domain adaptation algorithms for semantic segmentation have been mostly unsupervised, that is, requiring no annotation on the target side. They can be grouped under three main umbrellas. First, pixel level adaptation, which aims at aligning the input image space. Second, pseudo-level training, which aims at labeling the unlabeled target data using the source model and using it for adaptation. And third, feature or output space adaptation, which aims at aligning the output space between the source and the target domains. When we look at the plot of segmentation performance versus image annotation time on the target side, the strong fully supervised performance sits at the top right, requiring an enormous amount of annotation time, whereas the domain adaptation methods in the literature lie at the bottom left with no supervision. So there exists a considerable gap between the two. In this work, we utilize weak labels in two different paradigms of learning to bridge the gap while requiring none to low annotation cost. In this work, we use weak labels on the target side for adaptation. Specifically, we focus on using image-level weak labels. That is, given an image, we only have information about the presence or absence of the categories in the image, which are indicated as tick and cross here. There are two ways by which we can obtain such weak labels. We can estimate them using the segmentation model, which would be pseudo-weak labels. However, as this does not involve a human, using such pseudo-weak labels falls under the category of unsupervised domain adaptation. On the other hand, we can ask a human annotator to obtain the weak labels, which would be true labels and fall under the category of weakly supervised adaptation, which is first introduced to the literature in this work. Let's take a look at our framework for learning with weak labels. Given source and target images, we pass both through the network. On the source dataset, we use the pixel-wise segmentation loss. But on the target, as we only have weak labels, we apply a special type of global pooling to shrink the spatial dimensions and obtain a vector signifying the image level predictions over the categories. We then use the weak labels for the image to compute this image classification loss using binary cross entropy. Note that the domain gap generally varies across categories. With that in mind, we further use a category-wise domain alignment loss guided by the weak labels. Let's take a look at it in more detail. We first use the final prediction layer as spatial attention to pool the features from the penultimate layers and obtain category-wise feature vectors for both the source and the target domain. We then use category-wise discriminators to align the feature vectors between the two domains. For an image, we use weak labels to align only those categories which are there in the image, constituting the category-wise alignment loss. The discriminators are learned using the domain classification loss. Note that for each category, we have a separate discriminator, which are made of fully connected layers, and learned using only features pertaining to the respective categories. Such separate discriminators helps to adapt features when the domain gap varies across categories. Also note that as our framework is agnostic to the origin of the weak labels, it can be applied for both unsupervised and weakly supervised domain adaptation. Given this framework, we can directly use the weak labels which are acquired from the human oracle. But let's take a look at our procedure of learning in the unsupervised domain adaptation case where we have pseudo-weak labels. We first learn on the source images with pixel-wise segmentation loss, the green arrow showing the direction of backpropagation. After learning on the source for some iteration, we introduce the target images. In the forward propagation, we pass them through the network, obtain the image level predictions, and apply a threshold to obtain the pseudo-weak labels, which are denoted using a hat as they are estimated. Then we use the pseudo weak labels to compute the image classification loss and backpropagate it through the network. We further use the pseudo weak labels from the target with the weak labels from the source, which are trivially obtained given the pixel level annotations, and perform the category wise domain alignment on the target and backpropagate it through the network. We also learn the discriminators while freezing the rest of the network. Note that although we first discussed about using image level labels as weak labels, we can also use other form of weak labels from the human oracle. To investigate that, we utilize point labels, where we would ask the human annotator to click only on one pixel point in the image for each category that appears. We compute the cross entropy loss for only those few labeled pixel points and use it as an additional loss to learn the network parameters. Let's take a look at the results. Here is a plot of the target performance versus annotation time with the GTA5 as the source and cityscapes as the target dataset. When we use pixel level annotation on the target, it performs the best, but with huge annotation time. When we learn a model on the source and apply it on the target, we get the point at the bottom left with zero annotation time on the target. Then we have results of UDA methods from the literature. Our unsupervised adaptation method with image level pseudo weak labels performs better than other UDA methods in the literature. The values in the bracket indicate annotation time per image. In the WDA case, with Oracle weak labels, which is first introduced in this work, our model scores a significant performance boost with image level labels and furthermore with point labels. We find even further performance improvement using 3 point and 5 points annotated per category. It is interesting to note that the performance gap between unsupervised and full supervision can be significantly reduced with little increase in annotation time. We also see similar performance improvements for other cases, with different source dataset, with a different target dataset, as well as with a different neural network architecture. Here is an example with outputs from our model. Thank you for your attention and take a look at our paper and project page for more details.